In the real world, nobody reinvents the wheel. That is to say, everybody knows that the moment of inertia of a flat cylinder is 1/2 mr squared, and that's that. The real purpose of all these calculations in the parallel axis theorem is to work with flywheels, spokes, gears, and other mounted equipment that's meant to spin that is not a perfect symmetrical circle. Things that have other things drilled in it still have angular momentum, and we still would like to know the moment of inertia. Problem number 30 on your homework is a good example of one of these weird non-symmetrical flywheels. It's not spinning through its center, and it has a hole drilled out. This sounds like a perfect example to use negative mass. We'll have a moment of inertia, one big orange cylinder, and then a small white cylinder, which happens to have negative mass, which explains why it isn't there. That will be our moment of inertia, and if we can do that, we will be good to go. So, big orange cylinder, 1/2 mass of the big orange cylinder, which we were inconveniently not given, mr squared. Oh, wait, it's not rotating through its center. Hit up your parallel axis theorem. Fortunately, they give us exactly where the new axis was. The new axis was at r/2. There. So far, so good. Now the small one's much easier. The small one's rotating right through its center. It's a cylinder. 1/2 mr squared. But wait. This doesn't have a radius of big R. This has a much smaller radius of r/2, as given in the problem. Now, all we need to do is identify the mass of the big cylinder and the mass of the small cylinder, and we got it made. Let's do the small white cylinder first. What's the mass of the small cylinder? Well, the small cylinder, the one with negative mass that isn't there, has a radius of r/2. That's half the radius. That's a quarter of the area. That's a quarter of the mass of the big orange cylinder, the original one. Not the one we're given. We're given m, the mass of what's actually there. So I suppose we'll just have to find the mass of the big orange cylinder. Well, we're given m. M is what we have. What we have is the orange one minus the white one, which was a quarter of its size. That means what we're given is 3/4 of the mass of the big orange cylinder, multiplied by 4, divide by 3. We need to scale up our mass by a factor of 4/3. Watch. Take 4/3, take a quarter of them away. What do you get? Well, see, a quarter of 4/3 is 1/3. Take away 1/3. Poof, we have 1. There's the mass we have. Now, here's our m big and our m small, 1/4 m big. Let's see, 1/4 of 4/3. What did we say that was? Bless my soul. It was 1/3. Now it's just a matter of substituting. We have the moment of inertia of the bigger shape, 1/2. 4/3 m, r squared, plus another 4/3 m, r/2 squared. We have our moment of inertia of the negative mass, 1/2, 1/3 of the mass, r/2 squared. Subtract this from that, and you will get the total moment of inertia. All those fractions just get in the way of the fundamental principles. Once you've got the fundamental principles, then you can group fractions, find common denominators, and solve.